All right, so what do we mean by intermolecular force? What do you got?
Forces acting between different molecules.
How about we go particles? Because it could be atoms. Anything else you want to say?
They're not bonds.
They're what's responsible for the substance's state of matter. Okay, so surface tension for water, I'll just poorly draw something that looks like this. So where are the intermolecular forces? These little red dotty things that I wrote. So when those water skeeter bugs are skeeting around on top and they're not falling through, what is it that's keeping them afloat? Those little intermolecular forces. And when somebody jumps off the Golden Gate Bridge, what is it that they're trying to break through? Or I guess if they're jumping off the bridge, they're not wanting to break through them. But what stops them from going into the water? Those, right? Might not seem like a lot and depends on the situation, but there is obviously enough force there to cause problems depending on what your situation is. All right, so we've got methane. Maybe I should do this. Butane. I just don't have it in me to draw all the hydrogens. Okay, so here are these four molecules. They're just carbons and hydrogens, and they just get one carbon longer. And so what's the difference in the boiling points between the methane and the butane? Are they significant? Yes. So this here is a liquid at room temp, right? And this is a gas. Actually, all of these are gases at room temperature. When you buy a bottle of propane, when you purchase natural gas to heat your house or your water or something like that in your home, you're getting those first three, methane, ethane, and propane, not the butane. Why is it that the butane's boiling point is so much higher? So these guys have the opportunity to interact with each other over a greater distance. So the surface area between these two molecules is much, much larger. So they can, even though the intermolecular forces between them are weak, there are several weak connections as opposed to one or two or three different weak connections. As you add more carbons to it, you get more and more likely to be a liquid. You get up to 8. That one's obviously a liquid, right? What's the name for number 8 with 8 carbons? Give me the prefix at least. Okay, and then all of these end in what? So that's octane, yeah. And you obviously know that one being a liquid as it's gasoline. Now that you get to actually pump your own gas in Oregon. if the gas station says it's okay. What do all of these particular intermolecular forces have in common? Yeah. Yeah, I'll just go with that. Covalently bonded molecules, and then, yeah, that's fine. Okay, so what do we got for neon and xenon? What do we have? What do we have for the melting points? Oh, I guess I didn't actually ask you to write them down. I just said look them up. Okay, that's fine. So this one's higher, right? So I've got my little neon, and then I've got my pretty big xenon. And so explain why this one has a larger boiling point, melting point. What's a better word? Disperse. So here I've got 54 electrons that I can move back and forth across the molecule and make partial positive and partial negative. I've only got 10 electrons to move back and forth here. So at most I could get a partial positive or a partial negative here. That's based off of 10 electrons. Here I can get a partial negative and a partial positive based off of 54 electrons. So it's going to have a much larger partial charge. This is analogous to those dodgeballs we were talking about, being able to squish them or not. Hydrogen bonding requirements. What do you got? Obviously a hydrogen. Have to have this connection. But this one is boring. Why? That's it. And when I'm talking about that HF, I'm just talking about hydrofluoric acid. That's it. There isn't anything else going on with it. It's just hydrofluoric acid. These can be side chains on molecules that are billions of atoms long or 3 atoms long. And so why do these mix together so well? What are the molecules? At least you two should answer. Maybe they shouldn't answer, but they probably know the answer. Go on. What's that molecule I just drew there? You know the answer to this. Just say it.
Ethanol.
That one's ethanol, right? Drinking alcohol. And then the other one is water. We've talked about this in not just both polar. I agree they're both polar, but more than that. I've just met that requirement, right? These are molecules that undergo hydrogen bonding. So they really do want to stick together because this partial negative here and this partial positive here, this partial negative and this partial positive are very strong. So there's a very good attractive force here and here. So they're definitely going to mix with each other very well. They'll never separate based off of gravity or just settling.